Okay, third video. Sorry about that. I forgot to silence my phone before recording, so you got some cell phone call in there interrupting that one. So, uh, anyways, sorry about that. Hund's rule. We're talking about parallel spins. You got to do all the up arrows before you do all the down arrows. So it shows us that carbon would look something like this: 1s2, 2s2, 2p2. Nitrogen having 7. We would complete our third up arrow. Then it'd be 1s2, 2s2, 2p3. Oxygen with 8, we'd go back for the down arrows, and it'd be 1s2, 2s2, 2p4. Fluorine with 9, same thing. Neon with 10, same thing. You can really go through the whole periodic table like this if you wanted to. Here's the way you know the order to fill them in. You start with 1s, then 2s, 2p, and you keep them in a line: 3s, 3p, 3d, 4s, 4p, 4d, 4f. And then repeat out to f, then step down 1, and draw your arrows diagonally through them. And so the way you fill is you fill the 1s orbital, you get to the end of the arrow, you go to the next arrow. You fill the 2s orbital, you get to the end of the arrow, you go to the next arrow. 2p, 3s, go to the next arrow. 3p, 4s, go to the next arrow. And that's the order that you fill. You do not fill them 1s, then all your 2s, then all your 3s, then all your 4s. That's the wrong way to do it. That's not the most energetically efficient way that electrons want to be organized, and so we have to follow these arrows to show us how to fill electrons. And so here's another chart that would be quite a bit more complicated to memorize, but that gives you the idea. Okay, electron configuration is how electrons are distributed among orbitals in an atom. So 1s1 is our principal quantum number n, s is our angular momentum number L, and then 1 is our number of electrons that are in that orbital. And so our orbital diagram for that would be something like this: hydrogen 1s1 with the 1 up arrow. So what's the electron configuration of magnesium? If you're asked to solve a problem like this, go to your periodic table, find magnesium, find its atomic number. That tells you the number of protons. Number of electrons is going to be equal to the number of protons, assuming it's not some sort of ion, and it's going to be 12. And so then you go through and you start to fill. Okay, 1s2, then 2s2, then 2p6. Now we're at 10, and we fill 3s to 2, then we're at 12, and that's it. It really is that easy. Now you can use noble gas shorthand, where you go to the noble gas above magnesium, you find neon, and neon takes care of 1s2, 2s2, 2p6. So to save us some writing, we just write neon in brackets, and then 3s2. Alright, so what are possible quantum numbers for the last electron in chlorine? So you look at chlorine, you say it has 17 electrons. So we'd have to fill it in: 1s2, 2s2, 2p6, we're at 10, 3s2, we're at 12, 3p5, we're at 17, and the p orbital can hold 6, so we're fine there. And so we have 17 electrons. The last electron was added to the 3p orbital. So its possible quantum number would be n of 3, L of 1, and a magnetic spin could be -1, could be 0, could be +1, and it's angular momentum, and its magnetic spin could be either a +1/2 or a -1/2. Could be any of those. Okay, so sometimes you'll hear these periodic table chunks referred to as the S block or the P block or the D block. This tells you where your electrons are. All of your alkali metals are going to be 1s1, 2s1, 3s1, 4s1, 5s1. Your alkali earth metals are going to be 2s2, 3s2, 4s2, 5s2. The transition metals are going to be D orbitals when they're full of their number of electrons. Your lanthanides and actinide series is going to be F, and then here your non-metals and then a few of your metals are referred to as the P block. And then of course up here in your noble gases, helium is left out as an S block because it only has 2 electrons, so it's stable in the S. But if you hear asking about S blocks, P blocks, D blocks, this is what they're referring to. Here's the table you have in your book. It shows you a few different elements, their electron configuration, their atomic number, and then their noble gas electron configuration. So that's pretty easy to do. It's nice to use that noble gas configuration when you get something like out at the 7s kind of range, because you'd be writing for a really long time. So the last thing we have to talk about is paramagnetic and diamagnetic. The difference between the two is paramagnetic has unpaired electrons, and so here this would be an upspin, but they lack that downspin that makes them paired, so they're paramagnetic. Here's something that's diamagnetic. It has all electrons paired, so all of its outermost orbital, its p orbital, they're all filled with both an up arrow and a down arrow. That's what makes them diamagnetic. And with that, we